All right, let's discuss hypothesis testing with the world of the means. And in another video, I will discuss the hypothesis test of the proportions. So we'll cover both situations when sigma, the population standard deviation, is known and when sigma is unknown, which results in which distribution you're going to use, whether you're going to use a z or whether you're going to use a t. Okay, so prior to this video, we had 11.1, which was an introduction to hypothesis testing. And what was really important about that video was the focus on the setup of these hypothesis tests. You'll see today, as we go through the actual test, that the setup is so important because it determines the test and therefore the conclusions. So with an improper setup, you will be running the wrong test, and therefore everything after that doesn't make sense or doesn't answer the question. So let's discuss two different methods that you can go about doing hypothesis testing. With our guru, it does both at the same time, which is really nice because we'll see as I progress through this video, I'll show you first critical values and focus on that, then the p-value method and focus on that, and then I'll use them both in the remaining examples to show you how they're complementary, and they really should be both highlighting the same conclusion. If at any time they are showing you two different conclusions, it's most likely an error on the calculator's part, on our part. So not the calculator as a physical calculator, but us as a person. so let's run through a test by using an example. We're going to run through this step by step and highlighting all the different pieces that we need to know. So suppose the average national reading level for high school sophomores is 150 words per minute with a standard deviation of 15. A local school board member wants to know if sophomore students at Lincoln High School read at a different level from the national average for 10th graders. The level of the test is to be set at a 0.05, so that's that alpha level. Okay, remember that's the probability of a type 1 error occurring. A random sample size of 100 10th graders from Lincoln High School has been drawn, and the resulting average is 154 words per minute. If when I talked about alpha being the probability of a type 1 error occurring is not familiar, please go back to the 11.1 video on the introduction to hypothesis testing where I explain the difference between the two types of errors. Now, let's go through this. We're going to have to refer back to this slide quite a bit as we're just getting the hang of this, but let's see what our steps are. So our first step in running a hypothesis test is to determine the null and the alternative hypotheses. So recall from that introduction to hypothesis testing video that the null hypothesis, H sub naught, or H sub 0, remember naught is N-A-U-G-H-T, sort of like naughty, not. You can't not do this. The null hypothesis, it's really important that it has an equal sign, as this statistical test is designed to test that equal sign. And so we have two conclusions during the test, which we'll see. The conclusion on whether to reject or fail to reject the null hypothesis, and then the conclusion on the claim. Now, the claim is decided based on the wording of the test. So where did we come up with this setup? Well, if we go back to the situation, we look for what's being claimed or what's being asked to test. So here I see there's some statements being made. We have an average. Okay. A local school board member wants to know. Okay, so that's an indication that they're trying to run a test or claim that they want to know if sophomore students read at a different level from the national average. So we have the national average up here. The national average is 150 words per minute. And if the local school board member wants to know if it's different, that is a not equal to sign. So they're saying, I'm curious if the average at this particular high school is different from the national average of 150. So notice that labeling the claim is really important, and you'll see why as we get to the two conclusions at the end. It's very easy to forget which one was our claim, so it's easier if we know it right away. Also notice that the setup again is complementary, like we learned in the introduction to hypothesis video. So we have an equal and a not equal to sign. They're complementary signs. And this number is both set at 150. So we have the exact value of 150, and then the rest of the number line is here. So anything other than 150. We are doing a hypothesis test in the world of the means, so we'll use the population parameter mu. So here's how we determine the test. The alternative hypothesis will always be the one that determines the test. So here, look at this greater than sign. You see it looks like an arrow. It looks like it points to the right, which is why we would conclude, okay, if we have a greater than sign in our alternative, we are doing a right-tailed test, which means all of alpha gets stuffed in that right tail if we were doing the critical value method, which is what we're working on right now. If we had a less than sign in the alternative hypothesis, we would be doing, notice it points to left. To remind you, this is a left-tailed test. Stuff that alpha level all in the left tail. And if we're doing, like we are in this example, the not equal to sign, notice there is no pointing of direction, so that could help you remember that this is a two-tailed test, which means we take the alpha level and half of it goes into the left tail rejection region and the other half goes into the right tail rejection region. So if an alpha level was not specified, recall that the default is 0.05, just like the default for confidence intervals was a 95% confidence interval. Step 3, so step 2 was to, I don't know if I wrote it out. I did. Okay, sorry, I just skipped over it. Step 2 is to specify the significance level. So if it's specified in the problem, great. If it's not, we have a default, as I just read. If we go back to the problem, it was set at 0.05. So that's where we got the 0.05. Step 3 is to validate the assumptions of the hypothesis test and identify which test statistic we're going with, the Z or the T. So recall that in order to use a Z, we need to know the standard deviation for the population, and we need a sample size that is larger than 30, or the population is known to be normally distributed. In order to use a T, we would not know sigma, the population standard deviation. We would only know S, the sample standard deviation, and our sample size either needs to be large enough, which it typically isn't when we're using T. So we really need to make sure that it says it's from a normally distributed population. So is it quantitative data? Because hypothesis testing for the means needs to be quantitative data. If we're working with qualitative data, we really should be looking at the proportions world. Random sample used to obtain the data, that's always going to be a criteria that needs to be passed. If it wasn't randomly sampled, then we might as well give up now because the data is invalid anyway. Our sample size, was it larger than 30, or were we told the population is normally distributed? Well, I don't remember, so let's go back. And we have a sample size of 100, so it doesn't matter whether the population is normally distributed or not. Our sample size is large enough. And do we know the population standard deviation? Be careful. I think one of the largest mistakes I see students make is they say, well, I see the word standard deviation in the problem, so yeah, sigma's known. Well, that's not always the case. So notice here that they're talking about the national average, which is like everyone, the population mean word count. And in the same sentence, they say the standard deviation is 15. Now, if we look over here where they talk about the sample, they only give us the mean. Now, if they said the mean is 154 with a standard deviation of, let's say, 12, then that would be S. That would not be sigma, and we would be using a T. But because they did give us the population standard deviation, we're good to go. We can use a Z distribution. Step 4 in the process is to now go to our guru and run the test. So at this point, you should be taking notes on the steps of our guru or taking pictures or screenshots so that you have it in your notes. Once you get signed into our Guru, go to Analytics, Analysis, your mean inference for one population. So we don't have a data set, so we're going to fill in what we are given. So we're going to have to go back to the original problem here. Okay, our sample mean is 154. And we were not given the sample standard deviation. We were given the population standard deviation of 15. And the sample size is 100. Remember, we do have to label the variable. The mean is words per minute. Ooh, per minute. And let's test the hypothesis at a 0.05 alpha level. So notice that there's two tabs here. We were using the confidence interval for the last couple sections, but now we want to make sure we hit the tab of testing the hypothesis. Notice that they are only asking you to identify the alternative hypothesis, and that's because, again, the alternative is what determines the test. So our Guru knows that the null is always an equal sign, so it just needs to know what the alternative is. It looks a little funny here. This explanation point equal sign is the not equal to sign. Our Guru, hence the R, is written in R language, which is a programming language. So behind the scenes, it's all programming language behind this. And that is the syntax for R language for not equal to. So a little something different for you to learn. Now remember that the hypotheses were set to the national average of 150. And we are trying to determine whether 154 is significantly different to 150. If it is, we'll conclude that yes, the sophomores at this particular high school are reading at a different level. Although we aren't testing whether they're reading better or less than, we are testing different. So we can't make a conclusion other than yes, it's different or no, it's not. The Z statistic is the default, but remember, if we want to use a T, we have to unselect the Z and select the T, which we'll do in future examples in this video. Let's hit our eyeball. All right, so reading this screen, it gives us what we entered right up here. So this is just what we've typed in. Now down here, we are focused on the critical values method. So don't worry about this p-value. We'll talk about the p-value in the next example. We need these critical values. So because we determined it was a two-tailed test, there'll be two critical values, one on the left side and one on the right side. And these critical values define the threshold between the rejection zones and the fail to reject zones. So here, if your test statistic falls between negative 1.96 and 1.96, we will fail to reject the null hypothesis. So there should be a picture. Here we go. So here's the picture. So negative 1.96, 1.96 were the critical values found for a 95%, well, confidence interval, because it's two-tailed, it kind of lines up with those confidence intervals, or with the fact that we're using a two-tailed alpha 0.05. Now, these will not be the same if we do a one-tailed. Let's say we had a less than or greater than in an alternative, and we had an alpha of 0.05, it will not be 1.96. So be careful. It was only really standardized when we were working with confidence intervals. But here we are, we have our critical values. This pink region up here and the pink region down here is what we call the rejection region. If our test statistic is a number less than negative 1.96 or greater than 1.96, we will conclude to reject the null hypothesis. But if our test statistic falls between negative 1.96 and positive 1.96, somewhere in this greenish blue area, we will fail to reject the null hypothesis. So here's our test statistic, 2.67. The 2.67 is a number larger than our upper bound here, the 1.96, and therefore falls into the rejection zone. So we will be rejecting the null hypothesis. And recall the null hypothesis said that the averages were equal to 150, and we are concluding that that is false. So if our null hypothesis we're saying is false, we're rejecting this null, that means we're accepting this alternative, and we are going to say, oh, the claim that the sophomores at this particular high school have different scores than the national average is true, although we can't make any specifics about what that means. So observe that the probability associated with the level of the test is divided equally between the two rejection regions. So that's saying that that 0.05 alpha level was divided by 2. That's where we got 0.025. And that is the area on the left side, and equally that is the area in the right side for those rejection regions. The level of the test can be thought of as a tolerance for rareness. The level of the test defines the rejection region, which can be thought of as an intolerance zone. If the test statistic falls in the intolerance region, then the data has produced a sample mean that has in turn produced a test statistic that is too rare. Okay, this is really technical, but it's good to hear, even if it doesn't sink in. I pretty much cleaned it up a bit when I said you just take this test statistic and you see, you kind of play a game. Does it fall into rejection regions or does it not? But technically, this is what is happening behind the scenes. So it's good to know what is actually happening. So essentially, we lose faith in the null hypothesis if the test statistic falls in the rejection region. The data has cast too much doubt. Consequently, the null hypothesis is rejected. If it was in the fail to reject zone, then the test statistic, we would then be able to say that the null hypothesis will not be rejected, which we'll have some examples where that happens. So again, here we go, critical value on the left, critical value on the right. Okay, rejecting the null if there was a bigger test statistic, rejecting the null if there was a smaller test statistic, and failing to reject if it fell anywhere in between. But we saw that our test statistic was 2.67, which falls into that rejection zone. And we can conclude now that we know we rejected that null, and that means that we believe the alternative hypothesis, our conclusion states there is significant evidence at a 0.05 level that 10th graders at Lincoln High do not read at the national average. It would be tempting to conclude that they read above national averages, national levels, since the sample mean is considerably above the national average. However, we did not test for this. If we wanted to test for this, our alternative hypothesis would have had a greater than sign, and we would have to test whether 154 was significantly greater than 150 in order to make a statement that we believe the 10th graders at Lincoln High read above the national average. Now, I've included these critical value reference tables because I thought they might be helpful. I know that the Hawks Learning Homework likes to ask about critical values, and when you're using a Z, it's very simple because they're given in the actual test itself. But when you're using a T, it doesn't always give you that critical value. The T is a completely different chart though. So here are some reference tables for the Z, but I don't suggest that you use them. I suggest you just use our guru since it gives you everything that you need. Now let's talk about that p-value. So the critical regions is using critical values to define those regions and then kind of playing a game with the test statistic trying to see where it falls. The p-value method is a comparison between calculating the p-value and then comparing it to the selected alpha level. So a p-value is the probability of observing a value of the test statistic as extreme or more extreme than the observed one. Assuming the null hypothesis is true and all the assumptions related to the hypothesis test are satisfied. That probably made no sense, and that's perfectly fine. P-values are really not that clear or straightforward or obvious. They're a difficult concept to understand in depth quite frankly, it's one of the most controversial topics in statistics to this day, because too many people hold so much weight on these p-values when making their conclusions, and quite frankly, most of them use the p-value incorrectly. But anywho's, we're going to stay pretty basic as we are in an intro class. So what we need to know is that if the computed p-value, which our guru does for us, take a look, p-value, if it is less than the given alpha level, we conclude a rejection of the null hypothesis in favor of the alternative. If the p-value is greater than or equal to that alpha level, we'll fail to reject the null. So here, if we wanted to look back at this example, the p-value is less than 0.05, so it also would conclude with a rejection of the null hypothesis, confirming what we've already concluded with the critical values. Let's look at this example. So a microprocessor designer has developed a new fabrication process which he believes will increase the usable life of a chip. Currently, the usable life is 16,000 hours with a standard deviation of 2,500 hours. So let me stop right here to kind of emphasize what information we were given. So this line right here is talking about the overall population calculations. No mention of a sample was taken. So that's how I know it's population data. That means this is the mu and this is sigma. So sigma is given. Remember, that's important. When I'm doing these out on paper, I highlight this and I would label sigma as soon as I'm reading it, because the more I dissect a big paragraph of English when I'm trying to do math by labeling them with appropriate mathematical symbols, it makes the paragraph less English to me and more a mathematical model. I start building a picture in my mind. This tells us to test the hypothesis that the process increases the usable life of a chip. And they also specify the alpha level at 0.01. Increases, that's our key word for our alternative hypothesis, or for our claim, I should say. And I said the alternative because increases is a strictly greater than, it does not have an equal sign, and that's how I know it's going to go into the alternative hypothesis. A random sample of 1,000 microprocessors would be tested. Assume the standard deviation of the life of the new chips is equal to the standard deviation of the current chips. Okay, so this line right here is a little tricky. This is telling us that assume the population is normally distributed. It's another way of testing the distribution, which we don't even need because the sample size is ginormous. It's way bigger than 30, so we're good to go there. So determining the null and alternative hypotheses, again, you first translate that claim like we practiced in the intro to hypothesis testing video. That claim is increases beyond 16,000. So I write the alternative first, greater than 16,000, label my claim, and I create the complement. Now, technically the complement to the greater than sign is a less than or equal to, but it's really irrelevant at the point because the test really tests an equal sign. So whether you put a less than or equal to here or an equal to, it won't change the test. Specify the level of significance that was stated in the problem to be 0.01. Step 3 is to evaluate or validate rather the assumptions of the hypothesis test and determine whether we should be using a Z or a T. So was it quantitative data? Yes. Random sample to be obtained, assuming. Sample size was big? Yes. Sigma known, population standard deviation was indeed given, therefore we should be using a Z. Let's run a hypothesis test. And again, I'm going to come back to the original problem so we have the data in front of us. So I'm going to analytics, analysis, mean inference, one population. Again, I don't have a data set, but I know my sample mean. It didn't tell me my sample mean. Interesting. So it must be somewhere in the problem. I didn't catch that when I was writing this. Interesting. We're missing the sample mean. Let's just throw one in there then. Let's take this out. And let's say that the sample mean came out to 16,500 hours. Okay, we're going to make this up on the fly. Why not? So we have 16,500 hours as our X bar, our sample mean. So let's put our sample mean in here, which is 16,500. Our population standard deviation is 2,500. Our sample size is 1,000. The variable name is, we're talking about hours. And we're going to the test of hypothesis tab. A level of significance was chosen at 0.01, with our alternative being a greater than sign, greater than 16,000. We are using a Z because we have a large enough sample size and we have our population standard deviation. So when we click our eyeball, we see that we are working with either a critical value or a p-value method. Again, we get both. If we were using a critical value method, then here is the only critical value we need because this is a right-tailed test. Notice the greater than sign is pointing to the right, which is why the rejection region is only on the right side. See if we have a picture. Here we go. So, ooh, we have different values here. Oh, you know what? The values are going to be different because I deleted what their sample mean was. And I don't know what their sample mean was. So I just made it up. So this picture is no longer valid because this value is wrong. So let's pretend that this value for this purpose is 2.33, and that would define that this is the rejection region. And so if the test statistic was to the right, we would reject the null hypothesis. If the test statistic was less than 2.33, we would fail to reject the null hypothesis. So again, this picture has different values than what we have, but it's because I picked a random X bar and I missed whatever the X bar was in the original problem. So here our test statistic is 6.3. That is huge. That's way far into the rejection zone, way bigger than this number. And we can see that by this p-value. So recall this E-10 is calculator scientific notation. If we were to write it in human scientific notation, it would be 1.2698 times 10 raised to the -10 power. Essentially what this means is move that decimal place to the left because it's negative 10 places. And we would have 9 zeros in front of this one. And that's a really, really tiny p-value, way less than 0.01. Also leading us to conclude to reject the null hypothesis. So here our p-value is really small. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 3 if I round. Really tiny, less than the significance level, which leads us, we're still rejecting. So it looks like even though I randomly decided what the X bar should be, the mean, sample mean, we're getting the same conclusion, just a different p-value because we have a different sample mean than the problem originally wanted. Okay, we state our conclusion. So we said we're rejecting that null. Let's go back to our setup slide. We reject the null, which means we do not believe that the mean hours is equivalent to 16,000. That means that the alternative hypothesis is what we believe, and that's what our claim is on. So when we go to conclude with that claim, we'll state that there is sufficient evidence at the alpha level of 0.01 to conclude that the new fabricating technique is superior and leads to longer chip life. Next example. A personal researcher has designed a questionnaire she believes will take an average time of 35 minutes to complete. Suppose she randomly samples 20 employees and finds that the mean time to take the test is 29 minutes, with a standard deviation of 8 minutes. Determine if there is sufficient evidence to conclude that the completion of the newly designed test differs from its intended duration. Conduct the test at a 0.05 level. Assume the sample comes from a normally distributed population. Now here, they kind of gave us a little hint. They labeled this S, but even if they didn't label it S, we are in the sentence when they're talking about the sample. So see, they talk about, hey, there's a sample and we calculated a mean and a standard deviation. So it's all in one sentence, which is how we know, even if this was not labeled S, that the standard deviation given is not sigma. It is not the population standard deviation. So right there, I would highlight this and say, okay, because this is not sigma, I'm going to need to use a T. Besides that, I'm working with a really small sample size here. And so the fact that it says the population is normally distributed is key to this test actually running. So we would set up the null and the alternative. Remember, to do that, you have to identify what the claim is. So here it says, determine if there's sufficient evidence that the test differs from. Okay, remember, differs is a not equal to sign. So weirdly enough, our claims are always in the alternative for so far. That's not always the case. I happen to pick examples where all of the claims are the alternative. If they said, determine whether the completion time is the same as the national average, that would be an equal to, and the claim would be labeled in the null. But since they want us to test the differs part, that's the not equal to sign. So that's our claim. And we build our complement to be the equal sign with the null in 35 minutes. Specify the significance level. It was stated to be 0.05. Validate the assumptions and pick our test statistic. We do have quantitative data. Random sample, yes. Sample size is less than 30, but it was stated that the population was normally distributed. We do not know sigma, we only know S. We'll always know a standard deviation, but whether it was calculated from the entire population or just the sample is really what's important, which is something we talked about in the beginning of the semester. And I said that this is going to be crucial to word problems. And here we are, the wording is everything. So we are going to use a t-test statistic, and we're ready to run our test. So I'm going to go to Analytics and Analysis, Mean Inference, one population. I do not have a data set again, but I have a sample mean, which I will get from the original problem here. Here we go. Oh, nope, this was the other one. Where's the one I'm working on? Here we go. My sample mean is 29 minutes. My sample standard deviation is 8, with my sample size of a merely 20 employees. The variable here is time, so minutes, mean of completion time in minutes. Test for hypothesis significance level 0.05. Alternative hypothesis, we've decided to be that not equal to sign. And it is always going to be the population parameter set here. So never the sample mean in the hypotheses, never the sample statistic, always population parameter mu, because we're in the means, and the population average that we're comparing the sample mean to. We are using a T distribution. Remember to unselect the Z and hit the eyeball. So here we have, again, we can look at the critical values method, or we can look at a p-value. We are looking at a two-tailed test. It's two-tailed because the alternative hypothesis is not pointing in a specific direction. So we have our critical values of negative 2.093 and positive 2.093 as seen in this picture. If we see that the test statistic is a number smaller than negative 2.093 or bigger than positive 2.093, we will reject the null hypothesis. If the test statistic falls between these two values, we will fail to reject the null hypothesis. So our test statistic is negative 3.35. That is a number smaller than negative 2. And again, we're rejecting the null. That's not always going to happen, but it just happens to be the examples I picked. So we're rejecting the null hypothesis according to the critical values method. And let's follow that up to verify with our p-value method. So the p-value is 0.003, which is smaller than 0.05. So it also is concluding to reject the null hypothesis. So even though this is a t, we do get the critical value and the p-value in running a hypothesis test. Unlike the confidence interval, for some reason, the confidence interval test, as you saw in previous videos, our guru gives us the critical value for the z confidence interval, but not the t. Luckily here we have both, so we don't have to do any extra looking. And remember, degrees of freedom is always the sample size minus 1. So that's what DF is standing for. So I included the little chart here. If you are using a table before to find critical values, you look down the left side of the chart for the degrees of freedom and match it with your alpha level. In this case, our alpha level, this is for our one-tailed test, which the table isn't labeled, so that's kind of hard to use the table in this case. And 0.05 is our alpha level, but remember when it's two-tailed, it gets divided equally into the two tails, which is why the correct alpha level for this particular chart, which is a one-tailed chart, not a two-tailed, that's why we have to do the half of the 0.05 to get the correct critical value, which again, you don't have to worry about because our guru does for you. So using technology with the exact p-value according to the test statistic with the degrees of freedom is found to be 0.0034. Mine, we wouldn't be rounding to 4 in this, that's an overround. We make the decision, we are rejecting that null hypothesis based on both of the methods, critical value and p-value. So let's state the conclusion. Again, if we're rejecting the null, that means we are looking at that alternative as acceptable, which is that there is sufficient evidence at the 0.05 level to conclude the mean time to take the test is not 35 minutes. Again, you may be tempted to say it's more or less, but we didn't test for significantly more, significantly less. We just test for one or the other. So if you wanted to then say, well, 35 is much higher than 29, it looks like our sample is showing that we are way below a faster completion time, you would actually have to test that by making your alternative hypothesis a less than sign and rerunning the test. Let's move on to another example. So the Alexander Bolt Company produces half-inch A-class stainless steel bolts that have a mean tensile strength, we'll just go with strength, of more than 4,000 pounds per square inch, also abbreviated and known as PSI. This specified quality standard. Okay, so right here they are saying that, let's just keep reading. These bolts are primarily used in the manufacturing of farm implements. The company is very concerned about the quality and wants to be sure that its A-class product is above the quality standard. Okay, I just wanted to make sure, I had to read the whole thing before I made statements that may or may not have been true. So up here, they're talking about what the population outcome is. Okay, the population outcome strength is of more than 4,000 PSI. The company is making a claim. They want to know that the quality is above the standard. So we want to be greater than. Again, we're going to have a claim that's in the alternative because there's no equal sign for an above. There's a sample of 25 bolts that is randomly selected and tested for its strength. So we need to design a test, a hypothesis, determine if there's overwhelming evidence that the bolts are better than the specified quality standard given the sample values. So we need to create a data set for this one. So before we even move on to writing the hypothesis, let's actually get the data set in there so that we can run the hypothesis test when we're ready. So I'm going to go to data, I'm going to go to import data and create the data set. I'm going to label my variable name. These are going to be bolt strengths in PSI. And we need, they said 25 datas. Oh man, okay, this is a bigger data set than we're used to typing in ourselves. But that's okay, it's not too bad. So I like to create all my rows so I don't have to bother with that. 25. And I'm going to start typing 4023. Remember, the down arrow will keep your box live. If you hit enter, you're going to have to double click in each box separately, which is a pain in the butt. 3,993. And so on, I'm reading left to right from the PowerPoint and typing these in. I like doing this when class is live because then my students can tell me whether I made a mistake in my typing. So hopefully I either catch my mistake or you guys place in the comments that there's a mistake. 4055, 4004, 4049, 3995, 4019, 4003, 4029. Almost done. 40. I almost made this data set prior to recording, but I figured we always good review to remember how to put a data set into our guru because we get through so many sections and it's not always at the forefront of our mind. So this is good review. 3986. Oh no, that's not good. I'm missing a value. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Darn, I was hoping they just miscounted and they were wrong, but it looks like I'm wrong. So I need to find where my missing value is. So I'm going through one by one. Probably talking, looked up and forgot where I was. Happens a lot. Oh, I missed the 4,000. Okay, so I'm just going to put the 4,000 in the last one because it doesn't matter the order as long as they're all there. Okay, remember after you create a data set, you have to name it. So I'm going to say that this is 11.2 hypothesis test example. That works. Save as. Okay. So remember, every data set I make, I always go to the bottom of the data sets here, double click the new one I made to make sure that the labels are up here and the data values are in the cells. Very, very easy way to check whether you made a mistake or not, because 9 times out of 10, the mistake that we make is in the data set creation. So double checking is 2-second way of checking that it was in correctly. Okay. Now we got our data set in, let's keep going. We need to determine the null and the alternative hypothesis. So remember that they asked us to, the company their concern is that they want their product to be above the quality standard, which is 4,000 PSI. So the claim is that mu is greater than 4,000 PSI. The complementary hypothesis, the null, again, in this case, would be less than or equal to. It doesn't matter whether you write less than or equal to or whether you write the equal sign because the null is the statistical test. Step 2, identify the alpha level, and let's use 0.01. I don't believe it was stated, but the PowerPoint itself, the problem did state it here, so we'll use 0.01. Our assumptions, let's validate them. Are we quantitative? Yes. Are we randomly sampled? Yes. Now, because the sample size is less than 30 and nowhere in there did it mention that the population was normally distributed, a normality plot needs to be plotted. And we're looking for that the dots follow a linear line. If they don't show a linear pattern, then it would conclude that they do not come from a normally distributed population. Again, that's something that we explore in much more depth in an advanced stats class, but it is important to know how do we determine this if we had a sample set. And I'll show you in our Guru that our Guru produces the same graph. But again, it's not necessary at this level for us to really understand the depth of that. We're just looking for the linearity of this normality plot. Okay, the population is approximately normally distributed according to that graph. Our sigma is unknown. Well, that's a typo. That's not supposed to be an alpha. That's supposed to be a sigma. I'm just going to type it out, sigma. Ooh, that is very... Okay, so I will definitely go back and change those to sigmas in the PowerPoint, typo. The assumptions are met and we're using a t-test statistic because sigma is unknown. So coming over here to our Guru, let's go to analytics, analysis, mean inference, one population. This time we have a data set, so we're going to select whatever we saved it as. Once we do that, it should have imported this stuff. That's strange that it didn't. That's a first. Okay, let's try this again. Something went wrong. All right, let's close these windows. Analysis, mean inference, one population. Select our data set. Interesting. Okay, well, for whatever reason, it's not working. Normally, we would get a mean and a standard deviation from the sample with a sample size of 25. And it would calculate it for you. For whatever reason, it's not working. You know what? Let me try logging out and logging back in. And I love the fact that I get these problems while recording because it could happen to any of us. And I find that in some cases, if I log out and log back in, I get lucky. Oh no, did it not save? Okay, I'm not lucky today though, because it looks like my example I just saved didn't save, which seems to be my problem. All right, so sorry. I am going to have to quickly create the data set again. So this is drill, strength, and PSI. And again, I am making 25 of these. Well, if this happens to you, you can see that it's not just you. Sometimes our Guru has its glitches. Most of the time I find it's because I've been logged in for too long with inactivity, and then it just logs me out without telling me. So here I am thinking I'm still logged in and I'm not, and that's why it's not saving. So that's why logging out and logging back in should solve my problem. I'm hoping it does after I get these all plugged back in. So we are plugging in. Hopefully I don't make a mistake now that I'm rushing. So happy with it before, even though I missed one before. Hopefully I don't miss one again. Try not to. Here's the one I missed. Got that one in there. 3995, 4019, 1003, 4029. Last row. Make sure I didn't miss one. Thought I did for a second there. 40, 40, 40, 25. Whoops. And yes, I didn't miss any this time. 3986. Hopefully there's no typos. Save as 11.2 hypothesis test example. All right, so if you needed to see that twice, lucky you, you got to see that twice. Going back now, selecting the data set, please work. Oh, what is going, oh, okay, well, here we are. I needed to select the variable. Okay, so if you run into the issue, sometimes it is a logging out issue, but in this case, nice lesson to be learned. You have to select your variable so it knows what to calculate. All right, we're good. So we are calculated now. Let's get back to where we were. Here we are. So here, notice it already fills this in based on the variable name I've chosen up here. We have the sample mean comes out to 4,013, but what we're curious is that's significantly different than the 4,000. Standard deviation of the sample, which is S, not sigma. Sigma is unknown, which is why we will be using a t distribution. And we have a sample size too small, which is when you need to select these boxes. If you have a data set and you weren't already told that the population is normally distributed, make sure to select the T and unselect the Z and put in the correct hypothesis. They wanted to exceed this value. Ooh, and I think our alpha level was 0.01, but I can double check. Yes. Okay, so here is our normality plot that we saw in the PowerPoint. Again, all you're looking for is that the dots are following a linear line. And this p-value 0.298 or 0.3, okay, that is much larger than 0.01, which also tells you that this does satisfy that the data is normally distributed. Our hypothesis test is down here now that we know it's valid because our data is normally distributed. So let's see if I have a picture. Here we go. So we have a right-tailed test because we have a greater than sign in the alternative hypothesis. So we only need an upper critical value, which is a t-value. 2.49 is the upper critical value that marks the threshold between the rejection zone and the fail to reject zone. So if the test statistic is greater than 2.429, we would be rejecting the null hypothesis. If it's less than, we'll fail to reject. So we see that we have a test statistic of 3.43. They rounded it to 3.5, which is a hell of a round. But either way, it is much bigger than 2.49. So we will be rejecting the null hypothesis. To complement that decision, we look at this p-value 0.001, which is less than 0.01, and therefore concluding the same thing to reject the null hypothesis because we have a very small p-value. So since the value of the test statistic falls in the rejection zone, we are rejecting the null. Since the p-value is really small, okay, this rounds to 0.001, we will be rejecting the null. The secondary conclusion, which is referencing the claim, we can state there is significant evidence to conclude that bolt strength is above 4,000 psi. Notes. This comes from the ASA guidelines regarding p-values. That has to, ASA is the American Statistical Association. It's a nation or probably worldwide. I actually think it's worldwide. P-values can indicate how incompatible the data are with specified statistical models. Honestly, these guidelines, they're just something to think about, but they're not something you need to memorize. P-values do not measure the probability that the studied hypothesis is true or the probability that the data were produced by random chance alone. So essentially what we're reading right now are the common misconceptions about p-values. So they're trying to make clear statements here. Scientific conclusions and business or policy decisions should not be based only on whether a p-value passes a specific threshold. Okay, too many people put way too much weight on their p-value and are trying to make these broad conclusions that are, they're just, it's hard to explain, but they put too much weight on the p-value, and they really should be exploring other things as well. Okay, proper inference requires full reporting and transparency. A p-value or statistical significance does not measure the size of an effect or the importance of a result. By itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. So we are using both methods in conjunction with each other, which is really helpful for verifying our conclusions. And these 6 statements here, again, are things to keep in mind. And if there are like true or false questions in the Hawks Learning homework, these might be something to look at. But other than that, this concludes our very lengthy but informative lesson on hypothesis testing for the world of the means.